Hi there, I'm RYC. I'm a member of the Mathematics Discord. And last Friday on June 28th, I gave a talk about lax pairs. So this is the recording of that talk if you weren't able to make it or if you want to reference it and check it out. Um, so yeah, I'm going to go ahead and talk about this. This is just part one. Parts two and three are coming. I haven't given them yet. So if you're interested, check out the Math Discord. The events channel will have information about the parts, and we'll have links to notes from these talks as well as the links to these recordings. Okay, so with that said, let's get started. So today I'm going to be talking about lax pairs. And lax pairs are a mathematical tool that comes from linear algebra and ordinary differential equations. But they show up in all kinds of different places that come from physics. So for example, in classical mechanics, quantum mechanics, even things like nonlinear waves and general relativity, lax pairs show up all over the place. They show up in places in math too, for example, from dynamical systems, PDEs, and even areas of geometry like symplectic geometry. So today we're going to see how lax pairs come up in classical mechanics in the finite dimensional case. And then in the next two parts, we're going to see how lax pairs come up in infinite dimensions and some of the beautiful mathematical phenomena that are related to modern research that these interesting mathematical objects can show. Okay. So let's talk about the history a little bit, and then we'll get into talking about what a lax pair is. So lax pairs were introduced in 1968 by Peter Lax. Who was Peter Lax? He was a very, very big shot analyst, dynamicist. He studied a lot of different things about PDE theory and functional analysis. So Lax is well known for having worked here at NYU. He was a professor for a very long time here, and during that time, he did a bunch of interesting stuff. One of the main theorems that he's well known for is the Lax-Milgram theorem. This is a theorem from functional analysis that some of you may have heard of. Some of you won't have heard of it. It's something that you learn about in a first graduate course in PDEs oftentimes. And it's a very useful theorem for showing existence of solutions to various kinds of PDEs. It's very similar to the Riesz representation theorem for Hilbert spaces, if you know that. So aside from the theorems that he worked on, he's also well known for some of his great textbooks. For example, Lax's linear algebra textbook is a great textbook for people who are interested in analysis and want to learn linear algebra from that perspective. Goes into things like matrix norms and limits and things like that you wouldn't see in a typical linear algebra book. So highly recommend Lax's books, and his theorems are great too. So we're very proud of him at NYU, but this is just one of the things that he's well known for. So let's talk a little bit about lax pairs. So first of all, I have to tell you what a lax pair is. Well, a lax pair starts with two matrices, L and A. So L and A are going to be time-dependent matrices. So this R is going to be time. And at each time, we'll get a matrix. Okay. A is going to be a given matrix. And L is going to be unknown. And these two matrices together are going to satisfy a differential equation. Okay. So what will the differential equation be? The time derivative of L, so this L subscript T, is what I'm going to use for time derivative. This is the standard notation people use in PDEs. People also use a dot on top to denote time derivative in physics. Okay, so this I might also use a couple times as well because we're going to be talking about equations that come from physics, but these all just mean the time derivative. Okay, and remember that L is a matrix, which is each entry is a function of T. Then I should also mention that if we have second derivatives, we can have LTT, and we can also write L dot dot. Okay. All right. So this is our equation. And then we're also going to have an initial condition. So there will be some starting matrix L naught. Okay. And I should define for you what this guy is. This is the commutator of matrices, which is just LA minus AL. So we need to remember that matrix multiplication isn't always commutative. Many times, if you take two matrices and you multiply them one way, and then the other way, you get a different result. So LA minus AL will usually not be zero. And when it's not zero, L is going to change over time. Okay? So this is the lax pair. Now, this seems like a random equation that I just wrote down. It doesn't seem like it came from anywhere, but it has some nice structure to it. So you might think maybe it's worth studying this as a matrix differential equation, which is just to say it's a system of differential equations where each equation is for an entry in the matrix. Okay. So similar to how in ODEs we study systems of ODEs, which are just vector differential equations, this is a matrix differential equation. All right, and so where do these guys show up? Because it seems like they are a totally arbitrary differential equation I've written down. Well, it turns out that they show up in a bunch of different places. So in math, they show up in places like Hamiltonian dynamics, completely integrable systems, and symplectic geometry. And in physics, they show up in other places, like in classical and quantum mechanics. They're all over the place. And they even show up sometimes when we study things like waves and even general relativity. So lax pairs are really, really important, and it's important to understand how they work. So we're going to talk about different examples of where these show up from physics in a little bit. But before I do that, I want to say what we mean when a system admits a lax pair. Because most systems that we work with on a daily basis, especially in physics, involve quantities like scalars and vectors, but usually there isn't a matrix that's changing over time. So it's a little weird to say that, this is such an important differential equation when does a matrix even change in time? But it turns out that most of the situations in which we want to study lax pairs actually come from situations where we have vectors that are evolving in time. So typical differential equations, a typical system of differential equations, looks something like x dot equals f of x, okay, where f is some function that's potentially nonlinear, and we have an initial condition. And here, x is in Rn. Okay, so this is a system of differential equations, or a differential equation for a vector quantity x. All right, well, okay, I should say x is a function from time to Rn. And we say that this system here admits a lax pair, which is not always going to, but we say it does if there are functions s and t that take s and give you, or that take x and give you matrices. So we need that this gives you an equation of this form. Where L at time t equals s of x of t. So s is a function from vectors to matrices. And a of t equals t of x at little t. And we just need that the function from vectors to pairs of matrices, st, is injective. So that then we can recover our original vector x from the evolution of L and A. Okay? So this is what we need in order to say a system admits a lax pair. And this is a very kind of abstract way of writing it, but what it really just means is you take the components of x, you put them in matrices, and you see how those evolve. And then you can get back your vector x from the matrices that you put together. Okay? So finding lax pairs for systems that we already know the system, finding lax pairs for systems is a really useful thing to do. It's not always going to work, but when it does work, it'll give us a lot of information. And why is that? It's because lax pairs have a very beautiful property, which is that they have lots and lots of conserved quantities. A conserved quantity is a number or a scalar that doesn't change as time progresses. So from physics, we know things like conservation of momentum and conservation of energy. And we're going to see a lot of analogs to that here. Okay. So lax pairs have tons of conserved quantities. We're going to see what those are in just a little bit. And that helps us to really well understand the system. In particular, if you have enough conserved quantities, as many conserved quantities as the number of degrees of freedom in your system, then you have something called a completely integrable system. And a completely integrable system is a really important idea in dynamical systems because we can usually write down directly what the solutions to these completely integrable systems are, which is not something you can usually do with these general nonlinear differential equations. Okay. Now you have to write them in terms of integrals of some special variables, which is not the most satisfying explicit solution. but it is really, really helpful for understanding them analytically, and both as mathematicians and as physicists. So completely integrable systems are something we look for. Okay. And we'll talk a little bit more about properties of completely integrable systems later in the talk. Before we talk about that, let's go into some examples of specific lax pairs. And we'll talk about the ones that we plan on talking about over the next 3 lectures. So in part 1, we're going to talk about lax pairs from quantum mechanics or from classical mechanics. For example, the simple harmonic oscillator, which is a system that many of us will be familiar with. Then we're going to talk about some more interesting systems. For example, we'll talk about the Euler top, and there's also the Lagrange and Kovalevskaya tops. These are rotating tops that experience precession of the axis, and we'll see why lax pairs help us to understand this motion. And we'll also study something called the Toda chain, which I think I won't include in part 1 of this talk, just because when I gave this talk in person, I said that I would finish doing the Toda chain at the beginning of part 2. So I'm going to keep this in line with that, and we'll do Toda chain in part 2, along with evolution of a quantum observable. So that brings me to part 2 of the talk, which is quantum mechanics. Quantum mechanics is most well understood through the Schrodinger equation. And it turns out that the Schrodinger equation leads to a very, very nice lax pair for evolution of observables in quantum mechanics. And so what we'll do in part 2 is we'll talk about the basics of the mathematics of quantum mechanics, and we'll go from there to finding the lax pair that defines a lot of quantum evolution. Okay. And finally, in part 3, we're going to talk about lax pairs for PDEs. In particular, we'll talk about nonlinear wave equations like the KdV equation or the cubic nonlinear Schrodinger equation, okay, and how these systems are actually infinite dimensional lax pairs, which is a scary thing to think about. But these equations are really, really complicated. And having the structure as an infinite dimensional lax pair is great because it gives us a whole sequence, infinite sequence of conserved quantities that we can study for the system, and gives us a ton of structure on how they evolve. And so the property of a PDE being a lax pair is really, really important for doing modern research into these systems. There's even a lax pair that shows up in general relativity called the Belinsky-Zakharov transform. And it tells us that typical metrics that you see in general relativity, for example, the Schwarzschild metric, which is the way that space-time curves when you have a body of constant density that's a sphere in space. So if you have a sphere in space-time, constant density, it warps space-time in a certain way. And as that object moves, it brings with it this dent in space-time. And it turns out that this dent that it brings with it is stable, it's localized, it's well contained. That's very, very nice. Okay. It's something called a soliton, which, people call this a traveling wave. Okay. And it turns out that the Schwarzschild metric is a soliton. And that comes from the lax pair for the Belinsky-Zakharov transform. And similarly, the Kerr metric, which is when you have a black hole in space that's rotating, instead of a finite mass, finite radius solid body. This is also a soliton. So lax pairs come in handy all over physics. Let's just start with one of the simplest physical systems, the simple harmonic oscillator. Okay. So how do we study simple harmonic oscillator? Well, let's remember what it is first of all. We just have a spring and we attach a mass to it. Okay. And then we let the mass hang in equilibrium, and then we pull it down a little bit and let it go up and down. We're not going to study a damped spring. That will no longer admit a lax pair. But the spring without damping turns out to admit a lax pair. So let's figure out how to write it down, and let's see what it tells us about the system. We need to define some quantities first. So we have a mass m, and we also have a spring constant k. And we know that if we have a spring, or if we have a system evolving this way, the displacement x from equilibrium evolves according to this equation. So this is the acceleration of the displacement. And Newton's second law says that the mass times the acceleration equals minus k times x, which is the spring force. Okay. Now, an important quantity that'll come up is the frequency, which is square root of k over m. This is omega. And if we were to just solve this directly, we would end up finding that solutions look something like A cosine phi plus omega t, where A, the amplitude, and phi, the phase shift, are just constants. That can be anything. So the solutions look like sinusoids, okay? And that's for the height of the mass. Now, we don't actually care about solving the system here, though. We care about finding a lax pair for it and then seeing what that tells us. Okay. So one way that we can start to do that is we can write things down in different variables to try to make things a little more understandable. First of all, the lax pair is a first order differential equation, but this is a second order differential equation. So let's introduce some new variables in order to turn it into a system of first order differential equations. So I'm going to introduce u, which I'm going to call omega x. And then I'm going to introduce v, which I'm going to call x dot. Okay, so remember that's the time derivative of x. And then we can compute what u dot is. So that's omega x dot, but x dot is v, so that's omega v. And I can compute v dot. Well, v dot is x double dot, but that is minus k over m x. Okay, but k over m is omega squared. And then we can take one of the omegas and we can put it into x to get u. So this is minus omega u. Okay. And so what we found is that our system of ODEs has become u dot equals omega v and v dot equals minus omega x. Or sorry, omega u. All right, and this is another system of ODEs that you probably have seen if you've taken an intro ODEs class, because it can be drawn on the phase plane as orbits around circles. So again, if you've seen this, this is something that you might be familiar with. If you haven't, it's okay. Because again, this is not actually what we want to do. We want to find a lax pair for the system. So we have these new variables, and we can recover x from them just by taking u over omega. So that's fine so far. But now we need to put them into some matrices to try to get the lax pair structure. Okay, and we have two variables. So the smallest we can use is 2 by 2 matrices and have 4 spots. But that's too many degrees of freedom. So we can specify things in our matrices a little bit. Okay, so let's think about what L and A should be in order to get a lax pair LT equals LA that matches the system. Okay. If we wanted to have the same behavior as the system, we're going to need to do a few things. First of all, we can notice, and I'll write the dot here just so we can see that things are corresponding. Okay. First of all, we can notice that on the left-hand side, we have L dot on one side in one equation, and the other equation we have U dot and V dot. So if we want the left-hand sides of the equations to match, then the left-hand side of the lax pair, the L, should just involve U and V. And then that way, the time derivatives will be U dot, V dot. And so we probably just want the entries of L to be either U or V in each spot, or maybe with scalars. Because we have 4 spots and we have only 2 variables, we have some extra degrees of freedom. So what I'm going to do to make my life easier is I'm going to say, well, maybe we can make it so that L is symmetric and trace-free. So symmetric means that the top right entry and the bottom left entry match. And trace-free means that the trace of the matrix, the sum of the diagonal, is 0. And these 2 properties will be very nice for a lax pair. So I'm going to assume it because we have 2 extra degrees of freedom to restrict our matrix. And when I do that, there's not many options left because I already said that I'm just going to have U's and V's in entry. So we're going to write V minus V, and then we're going to write U and U. You can see that now the trace is 0, V plus minus V is 0, and it's symmetric. Okay, we could have put U's and V's in the opposite spots, but we're going to leave it like this for now, and we're going to see that it works. In reality, you would need to guess and check and see how you get a lax pair. There's kind of an art to finding these for different systems, and they don't exist for every system, so it's not easy to find. Okay. How about A? Well, we've got V's and U's on the left-hand side now. What about on the right-hand side? On the right-hand side of the lax pair, we've got an L already. And so the V's and U's and L are going to show up as first-order quantities, as degree 1 quantities on the right-hand side. Okay, so they're going to be linear in V and U. But in our original equation, we just had one V and U on the other side. So again, we want a linear relationship. So we need to have only V's and U's in L. If we had V's and U's in A, then we would end up with quadratic or higher order quantities in V and U, which we shouldn't have. So A will not depend on V and U. However, we do have the omega that we need to get into the system. Okay. And so A can depend on omega. And because there's only one omega on the right-hand side of our system in each of the equations, A should just have linear dependence on omega. Okay. One more thing to help us write down the lax pair. The commutator of two matrices, okay, has certain properties if the two matrices have certain properties. L here is a symmetric matrix, which I chose. And the commutator of a symmetric matrix and an antisymmetric matrix is still symmetric, which is good because L dot is also symmetric because it's the time derivative of L, which is symmetric. Okay, so that means that we should try to pick A to be antisymmetric. And that only leaves us with one real option for A, up to the constant. So I'm going to write a constant down. And an antisymmetric matrix, remember, if you take its transpose, its entries are negative of what they were. So the diagonal has to be 0. And then we're left with an omega and a minus omega on the diagonal. Because we said we needed linear dependence on omega. Okay, I've just written down two matrices based off of some heuristic argumentation. Now we need to see that they actually work as a lax pair. Okay, so how do we do that? Well, we can take the time derivative of L, and then we can take the commutator of L and A and see that they match, okay? As long as we pick the right value of C. Once we do that, then we know that our system evolves according to the right equation. And then what we can do is claim that our original harmonic oscillator emits a lax pair, okay? Because you can grab U and V, and therefore you can grab X out of the entries. So let's take the time derivative. Well, we have our equation for U and V. So the time derivative is going to be V dot, U dot, U dot minus V dot, which is minus omega U, omega V, omega V, omega U, okay, using our original ODE. And how about the commutator of L and A? So we've got this constant C out front that appears in both terms. And then remember, we need to multiply L by A. And we subtract multiplying A by L. Okay, so now let's actually write this computation down. When we multiply these two, we're going to get minus U, omega U, omega V, omega V, omega U, minus omega U, omega U, minus omega V, minus omega V, minus omega U. So I've just done the matrix multiplication. Okay, and then when we subtract these two matrices, well, we can notice that the right-hand matrix is minus the left-hand matrix. So we can turn that minus sign into a plus sign, invert all the signs, and we just sum the two matrices. And we get that this is 2C minus omega U, omega V, and omega U. Okay, but that guy was the same as this guy. So this is L dot, or LT. Okay, and so we see that, or sorry, I should write it's 2C LT. We see that if we pick C equals 1/2, so now we can choose the C. If we pick C equals 1/2, then we get a lax pair for the system. So we have shown that evolution according to this ODE, which was equivalent to evolution according to the harmonic oscillator, is also equivalent to LT equals commutator LA for L and A, which are given by these forms. So we say that the system admits a lax pair, and this is the lax pair it admits. Okay. Okay, we went through a lot of work there to rewrite the system we already knew how to solve in a way that seems a lot more complicated. We now have 4 variables instead of 1. So why did we do that? Well, it's because now we have introduced some conserved quantities. Okay? Our lax pair tells us what sorts of nice properties our system has. So let me give you an example of that. If we take L squared and then we take the trace, we're going to get something interesting that pops out. Now, the trace of L we already defined to be 0 by picking L to be trace free. But what about the trace of L squared? Well, L squared is equal to L transpose L. I happen to remember that the trace of L transpose L is the sum of the squares of the entries. So we get V squared plus U squared plus U squared plus V squared. Okay, and this is 2U squared plus 2V squared. And now we can substitute back in our equations for U and V in terms of X, omega, and X dot. And what do we get? I'm going to pull out a 4 over M. And we're going to be left with 1/2 M omega squared X squared plus 1/2 M X dot squared. Okay, what's this? This is the potential energy of a spring. This is the kinetic energy of the block in motion. And so we've gotten constant 4 over M times the energy of the system. And the energy of the system is conserved, according to physics. So E should not change in time. Okay, so I just took this random function of the matrix L, and I ended up getting an important quantity of the system that we couldn't see anywhere else. We couldn't see it from the original equation, and we didn't see it in the solution we wrote down. We didn't see it in the phase plot. It's something that only showed up when we took the Lax pair and we took the trace of L squared. So this raises a lot of questions. Why does the Lax pair give us conserved quantities like this? And why was taking the trace of L squared the right way to do it? So this brings us to part 2 of the talk today. And that is going to be about something called isospectrality. Okay. Lax pairs are isospectral, which is a property that means that as time progresses, the eigenvalues of L are going to stay the same. So I said at the beginning that Lax pairs have lots of conserved quantities, and the eigenvalues of L are conserved quantities of the system. Okay. So let's remember what eigenvalues are. So every matrix has eigenvalues and eigenvectors. Okay. So eigenvalues of a matrix are numbers, well, they're scalars, lambda. And eigenvectors of a matrix are vectors, psi. Okay. And they satisfy the eigenvalue eigenvector equation. Well, in this case, we have the matrix L. L psi equals lambda psi. Okay. Why is this an important equation to study? Well, it turns out that if you find the eigenvectors and the eigenvalues of a matrix, you can do something called diagonalizing the matrix. You can understand the matrix in terms of a basis of vectors where it is a diagonal matrix, and all it does is it scales each basis vector. Just like in this equation where we're applying L is scaling the eigenvector by the scalar lambda. Okay? So eigenvalues and eigenvectors are very important. And knowing that the eigenvalues of a matrix are conserved is very, very useful for understanding how it evolves in time. Okay, so let's try to prove that Lax pairs give us isospectral matrices, that L has the same eigenvalues for all. Well, in order to prove that, we're going to start by trying to understand what we need to prove. Okay, so we're not going to start the proof yet, but we're going to start by trying to understand what is it about Lax pairs that might have the isospectral property. And the only thing that we can do at the start is taking the time derivative of the eigenvalue eigenvector equation. Okay, so let's do that. Now, we should remember that for vector matrix multiplication, the product rule works just the same as it does for function-function multiplication. So that won't be a problem. So let's take the time derivative of the eigenvalue eigenvector equation and see what we get. So I'm taking the time derivative and I'm applying the product rule. So on the left-hand side, we get LT psi plus L psi t. And the right-hand side, we get lambda t psi plus psi lambda t. And if we want to show that lambda is conserved, we need to show that the time derivative of lambda is 0, so that it's constant in time, okay? So this is what we're trying to show. Okay, what can we do with this equation that we just differentiated? Well, all we know is we know the Lax pair. LT equals commutator of L and A. Okay, so let's apply that. LA psi minus AL psi plus L psi t equals lambda t psi plus psi lambda t. Sorry, plus lambda psi t. I should have written this better before. There we go. Lambda psi t. Okay. And yeah, so I applied the product rule incorrectly before, but I just fixed it now. Okay. And what we can do is we can move over the, well, okay, the first thing that we want to do is we want to use the eigenvalue eigenvector equation in order to replace L psi with lambda psi. And then because lambda is a scalar, we can pull it out. Okay, so we get LA psi minus lambda A psi plus L psi t. And the other thing I'm going to do is I'm going to move lambda psi t over to the left-hand side. So I'm going to get minus lambda psi t equals lambda t psi. Okay, and we have two more steps here. So we're going to factor out an A psi from the first set of equations, or from the first set of quantities. And we're going to factor out a psi t from the second set of quantities. Okay, and what we'll be left with is L minus lambda times the identity matrix. So lambda identity times psi is just equal to lambda times psi times A psi plus L minus lambda times the identity matrix psi t, which is equal to lambda t psi. And finally, we have the same matrix on both sides here, so we can factor it out. And we get L minus lambda I times A psi plus psi t is equal to lambda t psi. Okay. So we have found now that if you have a matrix that's evolving with time, with eigenvalues, with an eigenvalue lambda and an eigenvector psi, that it evolves according to this equation. Okay, that the eigenvalue, the time derivative of the eigenvalue can be found in terms of the time derivative of the eigenvector. Okay, so here we've written down an evolution equation, and it indicates to us that we might want our eigenvector. So if we want lambda t to be equal to 0, then we want the left-hand side to be equal to 0 as well. And so in particular, we want A psi plus psi t to be in the kernel of the matrix L minus lambda I. Okay, so what does it mean to be in the kernel of L minus lambda I? It means that you're an eigenvector of L with eigenvalue lambda. Okay, so we want A psi plus psi t to be another eigenvector with eigenvalue lambda. Now, it's going to turn out that we can actually make A psi plus psi t equal to 0. Okay, and let's see why that is quickly. Well, let's start by just studying what happens if A psi plus psi t is equal to a constant times psi. So we'll assume that lambda is a simple eigenvalue, that the only eigenvector of with eigenvalue lambda is multiples of psi. And so that means that if A psi plus psi t is in the kernel of L minus lambda I, that A psi plus psi t is just going to be a constant multiple of psi. So this isn't always true, but we're going to assume it's true for now. And then later we'll get rid of that assumption. Okay. So what happens if we have an equation like this, where C here can depend on time? Well, we can rewrite to see that psi satisfies an ODE. Okay. But it turns out that the C here doesn't matter. And why is that? It's because LT equals commutator of L and A, but LT also equals the commutator of L and A minus CI. Why is that? It's because if we just look at the CI part, LCI minus CIL is just equal to CL minus CL is equal to 0. L times a multiple of the identity is always, or L always commutes with a multiple of the identity. Okay. And so that means that it doesn't matter if we replace A with A minus CI. The evolution of L won't change. L will be the same matrix no matter which A we use if we add or subtract a multiple of the identity. Okay, so A here, remember, was a given. So what we do is we change A to A minus CI. We relabel, we just say that that's A again. And now we have a new evolution equation, but L is going to stay the same as time goes on. Okay, so this doesn't change the behavior of L. And because the eigenvectors just depend on L, it doesn't change the behavior of the eigenvector. So in particular, this CI doesn't matter here. Okay, so we can just replace this by a new A. All right. So this is a little bit of a tricky sort of thing we can do. And you might ask, well, shouldn't A minus CI have a different evolution? And the answer is yes, it does. But it turns out that the eigenvalue that you get from that, so the eigenvector, sorry, that you get from that is in the same direction, but it's just scaled. Okay, so you can study all this and make sure this is true. But this is something that we can do. We can wipe out the C and we can assume that actually psi t plus A psi is equal to 0 instead of C psi. Okay, just by factoring that C into A. Okay. So this is the first step. And what we're going to do next is we're going to actually prove that the Lax pair is isospectral. Okay, so let's go ahead and prove that the Lax pair is actually isospectral. So in order to do that, what we'll do is we'll start with this equation. And we're going to start over from scratch. Now we're going to say that psi is just any vector. It's going to be a vector that follows this ODE. And then we're going to prove that psi is actually an eigenvector. Then once we prove that psi is an eigenvector, we'll see that the eigenvalue is going to be constant in time from what we did before. Okay, so let's go through that step by step. So psi here is a vector that evolves according to this equation. So let's write down the exact ODE it solves. So what we'll do is we'll start with an initial condition. L naught psi naught equals lambda naught psi naught. So psi naught is going to be a vector, which is an eigenvector of L naught with eigenvalue lambda naught. And then what we'll do is we'll have psi evolve in time according to the equation above. So psi t is going to be equal to minus A psi with the initial condition psi 0 equals psi naught. And what we want to show is that for all time, psi is an eigenvector of L. Okay. And once we show that, we'll have shown that eigenvectors evolve according to this equation. All right. So how do we show something like that? Well, all we can do is we can look at L psi. And we want to show that L psi is equal to lambda naught psi, or is equal to lambda psi for all time. So let's take the time derivative. And when we take the time derivative, we can apply the product rule. This is going to help us see how L psi evolves. Okay. So when we take the time derivative, we apply the product rule. We get LT psi plus L psi t. Okay. What does that give us? Well, LT we know satisfies the Lax pair. So this is LA psi minus AL psi. And for the second term, psi t evolves according to an ODE. So we know that we get L, and then we get a minus A psi. So I'm going to put the minus sign here, and we get psi. And look at this, we get a cancellation. And we're left with minus A times L psi. Okay, and so what does this mean? This means that L psi satisfies the following ODE. Okay, and what's the initial condition? L psi at time 0 is just lambda naught psi naught. But this is interesting because this ODE and this ODE are actually the same ODE. They're both a vector evolves according to minus A times that vector. Now, the problem is that they don't share the same initial condition. But because the equation is linear, we can make them share the same initial condition. So how do we do that? Well, if we divide everything we just did by lambda naught, because lambda naught is constant in time, it just comes out of all the time derivatives. Okay. And what we end up finding is that L psi over lambda naught equals minus A L psi over lambda naught. And L psi over lambda naught does have the same initial condition as psi. Okay. And this is great because now we can use uniqueness of ODEs. Uniqueness of solutions to ODEs says that if you give me an ODE that has, or a linear ODE, okay, that has the same initial condition and the same equation for two different variables, then the two variables will be the same for all time. Okay. So uniqueness of solutions to ODE says if you have two solutions that have the same initial condition for the same ODE, then they're the same solution for all time. And in this case, that means that psi t is equal to LT psi t over lambda naught for all time, which is really useful because we multiply by lambda naught, we get that L psi equals lambda naught psi for all time. And that tells us that psi, if it evolves according to this equation, is going to stay an eigenvector of L for all time. And moreover, it tells us that the eigenvalue is always going to be lambda naught, which was the starting eigenvalue. So the eigenvalue doesn't change over time. Okay. We can also look back to what we derived before. We now know that for eigenvectors, A psi plus psi t is equal to 0 because that's the equation they evolve by. And so therefore, L minus L lambda I times 0 is equal to 0. And therefore, lambda t is equal to 0 because eigenvectors are never 0. And that tells us the eigenvalues are all constant time. Okay, so we've shown that the Lax pair is isospectral. Now, in order to do that, we assumed that we had a simple eigenvalue, but it turns out that we can do this without that assumption by taking what we just learned about evolution of eigenvectors and writing it down in a matrix. So say that L naught is a diagonalizable matrix. It diagonalizes according to something like this. So lambda here is the matrix of eigenvalues of L naught on the diagonal. S naught is the matrix whose columns of L whose columns are the eigenvectors of L naught. Okay. And as long as we can write our matrix in this way, just like how we evolved our eigenvectors, we can evolve S. So we'll define S for all times by the following ODE, which says that ST is equal to minus A times S. And if we do that, then we'll find that if we define L of t as S of t, lambda naught S of t inverse, then L will satisfy the Lax pair. So this is the solution to the lax pair. And now, as long as you can solve this equation, you know how to solve the lax pair, okay? But more importantly, what this tells us is that L of t is a similar matrix to L naught for all time. And that means that they have the same eigenvalues. So let's see why this L of t is a solution to the lax pair. Well, we can differentiate and apply the product rule. So LT equals ST lambda naught S inverse plus S lambda naught T S inverse plus S lambda naught S inverse T. Lambda naught is constant, so this term is just 0. The first term, we can apply the evolution of S to get this is minus A S lambda naught S inverse. Okay. For the second term, we need to figure out how to differentiate the inverse of the matrix in time. So let's do that on the side. So what we know is that the identity is equal to S inverse. So if we differentiate this in time, well, the identity is constant. How do we differentiate the right-hand side in time? We apply the product rule. Okay, and now we know that 0 is equal to ST S inverse plus S inverse T, and we can solve for S inverse T. So what do we get when we solve? We get a minus sign, we have to multiply by S inverse, and we get ST S inverse. Okay, so let's plug this in. We get S lambda naught, S inverse, ST, we can apply the equation, minus AS, S inverse. Okay, and then now we need to simplify things. Let's use that S lambda naught S inverse is equal to L. Let's also use that S and S inverse cancel. And we'll get minus AL. And here I should have had a minus sign. Wait one sec. Yeah, I should have had a minus sign. Because we get a minus sign from minus S inverse ST S inverse. So we get double minus sign, they cancel, and we get L times A. And this is just LA minus AL, which is the commutator. And so we've checked that defining L by ST lambda naught S inverse satisfies the lax pair, okay? And that means that L of t has the same eigenvalues for all time, even if it doesn't have simple eigenvalues. Okay, well, this is only true for diagonalizable matrices. You can then go on to study Jordan form matrices and things like that. Okay? But this is what we're going to stick with for now, because our L's are going to be either symmetric or antisymmetric. They're going to be diagonalized. Okay. So we've shown that the lax pair is isospectral. What does this mean for us? Well, it means, like we said, the eigenvalues are conserved. They don't change in time. But it also means that some easier to compute quantities are conserved. For example, the trace of the powers of the matrix. So remember that the trace of a matrix is equal to the sum of the eigenvalues. So if the eigenvalues are conserved, the trace is also conserved. And similarly, if you take powers of the matrix, you get powers of the eigenvalues. And so the sums of the powers of the eigenvalues are conserved. So that means that the trace of L to the k for any k is conserved. So this is a lot easier to compute than computing the eigenvalues, which requires us to find the roots of the characteristic polynomial in general. Okay, so that's one thing that we can get. Another thing that we can get is that the determinant of the matrix is conserved. That's just the product of the eigenvalues. Or we can also look at the coefficients of the characteristic polynomial of the matrix, which again, only depend on the eigenvalues. So these are various conserved quantities that we can get out of our matrix. And some of them might depend on the other ones, okay? But if we can get enough of these to be independent, we can put some really, really strict restrictions on the behavior of our system. So finding a lax pair for our system turns out to be really useful because we can immediately compute a bunch of these conserved quantities, and then we can figure out how many of them are independent and get lots of restrictions on the behavior of our system. If you get n restrictions on a system with n degrees of freedom, then you have something called a completely integrable system. which restricts the motion to these sets called invariant tori. Okay? They're literally going to be tori, either a circle, 2D torus, 3D torus, et cetera, et cetera. And on each of these tori, each torus is defined by picking each of the conserved quantities. That limits you to a sort of surface in the phase space. And on that surface, you move around according to something called action angle coordinates. And you end up with solutions showing something called periodicity or quasi-periodicity. So they wrap around these invariant tori, and they either come back to where they started and they're periodic, or they fill in the whole torus densely as time goes on. And that's called quasi-periodic, if they never come back to where they started. So these are the two kinds of behavior you can get for completely integrable systems. And you can study things like the action angle coordinates and et cetera, et cetera. So if you're interested in this, you should definitely go read more about completely integrable systems. It's a really beautiful field. You can study things like, for example, why if you perturb the solar system slightly, it doesn't suddenly become chaotic and fall apart. This is called KAM theory. So completely integrable systems have a lot of beautiful properties that come from different areas of math, like symplectic geometry and Hamiltonian dynamics, and lax pairs are one way of getting. Okay. So let's move back to studying some examples from classical mechanics. This is the last example we're going to talk about today, the Euler top. And then next time we'll talk about the Toda chain and we'll talk about quantum mechanics. Okay. So what is the Euler top? So we have a body in 3D space. So right now we're not going to have gravity. It's just going to be floating and rotating around its center of mass. Okay. But the body can be irregularly shaped, and it can even have an irregular density. And we want to find out what happens to the angular momentum of the body over time. Well, we know that the angular momentum is conserved, and we're going to see that through the lax pair. But what we really want to find out is what happens to the axis of rotation, the angular velocity. Okay. So if you try spinning an object in space and then you poke it, then you're going to notice that the orbit of the angular velocity vector, the axis on which it's spinning, is going to move around in a circle. Okay. And so this has something to do with conservation of angular momentum and et cetera, et cetera. Maybe you did when you did, your physics class in high school, you did some problem about rotating tops and you tried to understand this. Turns out that lax pairs are going to give us a really, really nice way of understanding the precession of the angular velocity. Okay, so what's the setup? We have some angular momentum vector in green here, S, which is conserved. And we have this angular velocity vector, which is the rotational axis of our object. And what we want to do is we want to see how the angular velocity vector moves. Well, instead of doing that for our purposes, we're going to pretend the angular velocity vector is fixed, so the body is fixed itself, and the angular momentum vector moves around it. So this is just going to be a set of coordinates that is called fixed body coordinates. And we're going to see how the angular momentum vector evolves. And then we'll switch back to the angular momentum vector staying fixed. All right, well, we know from physics that angular momentum is conserved. So how do you get equations for what happens when you fix the body instead and let the angular momentum vector move? Well, there's some change of coordinates that you can do that tell you something called Euler's equations, which I'm not going to derive, but you can look at this on your own, which tells us the angular momentum vector evolves according to a cross product of the angular momentum vector with the angular velocity vector. Okay, so now we have to remember our cross products, which is a little annoying. Okay, so we have this equation for the evolution of the angular momentum vector, but we have two variables, the angular momentum and the angular velocity. And what's the relationship between the two of them to close this equation? Well, it turns out that they're related by something called the moments of inertia. So we have something called the inertia tensor, which is a 3x3 matrix, Ij, which is defined by some integral. So I'm just going to write down this delta is the Kronecker delta. So it says when I equals j, it's 1, and when I is not equal to j, it's 0. So that quantity gets multiplied by the density, rho, and you integrate it over the object. So this is over the object. And you get entries of this 3x3 matrix I. called the moment of inertia tensor. And it's a symmetric matrix. So what we're actually going to do is we're going to reduce to the so-called principal moments of inertia, I1 and I2 and I3. So pick an eigenvector basis for I. Okay, so what I'm saying here is I is a symmetric matrix. It has a basis of orthogonal eigenvectors. And so we pick those eigenvectors, we put our fixed body coordinates into those eigenvectors, and now our moment of inertia tensor is just going to be diagonal. Okay, so in each of the directions, we have a different moment of inertia, I1, I2, and I3. And we can do our evolution in this basis. And why is this moment of inertia tensor useful? Well, it tells us the relationship between S and omega. S is just equal to I times omega. So again, this comes from physics. And it couples S and omega so that our Euler equation is closed. Okay, so let's actually get to finding a lax pair for the system. How do we find a lax pair? Well, one thing that we can do is we can convert these cross products into commutators. And this comes from something called the SO3 representation of R3. Okay, so R3 with the cross product turns out to be isomorphic as a Lie algebra, which is a fancy object in something called Lie theory in math, to the algebra of antisymmetric 3x3 matrices, which is SO3, little SO3. So this is a Lie algebra because when you take two matrices that are antisymmetric and 3x3, and you take their commutator, you get another antisymmetric 3x3 matrix. Okay. So this is what we mean by Lie algebra. And it turns out that the cross product in R3 is isomorphic to this guy. What's the isomorphism? You just take the entries of your vector and you put them in the right spots. So 3x3 matrices have zeros in the diagonal. And the isomorphism here is going to be S3 minus S2, S1 minus S3. It has to be antisymmetric. So this is S2, this is minus S1. And similarly, we can do this with omega. Okay, and once we've put the right entries into the right spots for L and A, we find that S cross omega immediately turns into L commutator A. Okay, and I should have written L's here. All right, so this is a lax pair for the system because we originally had ST equals S cross omega, and we converted it directly into LT equals L commutator A. Now, if you want to check that this is the isomorphism, then you just have to do a little work to multiply L and A and L and subtract and see that you get the cross product of S and omega in your resulting entries. Okay, so this is great. We found a lax pair for the system really quickly, but it turns out that this lax pair is actually not all that useful. And you can get a hint of that from the fact that we haven't used the moment of inertia tensor at all anywhere. Okay. So let's compute what the traces of the powers of L are. Well, the trace of L is just 0 because it's antisymmetric. The trace of L squared, that's going to be the sum of the squares of the entries with a minus sign. Which is just the total angular momentum. So we know then that the total angular momentum is conserved, which is great. What about the trace of L cubed? Well, as an antisymmetric matrix, it turns out this is actually going to be 0. Okay, and we start to run into a problem here. We think, what about the trace of L to the 4, et cetera, et cetera? Are we going to get anything new? Because right now we only have one conserved quantity, but we have 3 degrees of freedom. So this isn't good. And so you might be inclined to say, maybe I can compute the eigenvalues of this matrix and just see if anything else will come of it. And if you compute the eigenvalues, what you'll find is that there's 0 and plus and minus I times the total angular momentum, which tells us that all we can find out of the conserved quantities of this matrix are the total angular momentum is conserved. Okay, because it's the only thing that's new in the eigenvalues. So we don't get that much from this lax pair, which is pretty annoying. Okay. So I'm going to call this L1 A1. Let's look for a new lax pair, L2 and A2. And this time we're going to try to include the moment of inertia tensor. Okay. So we'll just do this arbitrarily. Okay. How do we do this? So let's try taking L2 to be a modification of L1 plus some function. I'm going to call the function K of the moment inertia tensor. This is going to be a matrix. Okay. And we'll take let's take A2 to be A1 plus some function of the moment inertia tensor. Okay, and then if we want to get a good lax pair out of this, we need that L2 time derivative, which L2 time derivative is just, I'm going to erase this for now. L2 time derivative is just L1 time derivative plus 0 because I is conserved over time. Or, I doesn't depend on time, just a constant. So we need that to be equal to the commutator of L1 with A1. And, so we know that that is equal to the commutator of L1 and A1. But what we want it to be equal to is the commutator of L2 and A2, which is commutator of L1, A1, I'm just expanding, plus Ki commutator with A1, plus L1 commutator with Ji, plus, what's the last one here? It is Ki commutator with Ji. Okay, and then we need these two to cancel, so we need all this to be equal to 0. All right, so how can we guarantee something like that and get non-trivial K and J? And then we'll get a new lax pair. There's a lot of freedom here. There are a lot of different things we could do. Okay, so I'm gonna erase these quickly, give me some space. Okay, so one thing that we can do is we can use our relationship between S and omega. And what that tells us is that because L1 was related to S and A1 was related to omega, that A1 is actually, or that L1 is actually equal to I times S1, or to A1. So this is just true. You can check it. And if we use that, then we can plug in I A1. Okay. And let's say that we want these two to cancel. If we want these two to cancel, then what we should do is we have an extra power of I here, and we have one power of I here. And that means we need two powers of I here. So maybe we should assume that K is equal to J squared. So that in both terms, we have the same power of I. And that J, I should say, is linear in I. So again, I'm making assumptions here with the hope that I'm going to get a good answer because we have a lot of extra degrees of freedom here. K and J are both matrices, so we have 18 entries, and we only need to satisfy one equation. So we have a ton of room here to screw around. Okay. So if we want this to be the case, then we can maybe assume that K could be equal to J squared and that J is linear in I. And then we would get the right powers of I on both sides. And the other great thing about this is that if K is equal to J squared, then K and J can be, okay? Because J squared times J equals J times J squared. So this guy just becomes 0, and we just need these to cancel. Okay, so this gives us some equations we can write down, and we'll end up finding that we can even take J to be a diagonal matrix. What is the diagonal matrix going to look like? It's going to look like I2 plus I3 minus I1, I1 plus I3 minus I2, and I1 plus I2 minus I3. with the zeros on the off diagonal with a 1/2 out front. And if you pick this matrix J that depends on I, then you get a new lax pair, which is given by L2 equals L1 plus J squared. And A1 or A2 is equal to A1 plus J. Okay, and as we checked by computing this J, if you take the commutator, then you're going to get that, what I should say is J squared A equals minus J squared A1 equals minus L1 J, which means that we end up with L2T equals the commutator of L2 and A2. Okay, so we've got a new lax pair for the system. This time it involves the moments of inertia. Let's see if it gives us any new conserved quantities. So as before, the trace of L is just equal to 0, so that's not useful. The trace of L squared is new. Okay, so the trace of L squared is going to turn out to be the trace of J to the 4, which is just constant in time, so we don't care about that, minus 2 times the total angular momentum squared. Okay, so this guy tells us that, again, the total angular momentum is conserved. Why? Because this is conserved in time, and this is conserved in time. So that means this is conserved in time. And now let's take the trace of L cubed, and let's see this time if we get 0. Well, it turns out that instead, we're going to get something like this. So you should compute this yourself. We'll get the trace of J to the 6 minus 3 times trace of I squared times the total angular momentum squared over 4. So this guy is conserved, this guy is conserved, this guy is conserved with time. But we're also going to get this. Determinant of I times 1/2 S1 squared over I1 plus S2 squared over I2 plus S3 squared over I3. And this quantity we're going to call E. It turns out that this is the energy of the system, the kinetic rotational energy of the system. Okay? If you go ahead and compute what the units of S1 of angular momentum squared over moment of inertia are, you're going to get units of energy. And because this is conserved in time, this is conserved in time, and this is conserved in time, and determinant of I is constant in time, E is a new conserved quantity. So we did it. We got a new conserved quantity by modifying the lax pair. Okay, so we've recovered the energy. Now, we did all this work just to recover the energy, which is great, but you might wonder, what does this tell us about the evolution of the problem? Well, it actually tells us something really, really interesting. And why does it tell us that? Well, the energy looks like the equation for an ellipse. If you have the energy is equal to a constant, then you're defining the equation for an ellipse in the space S1, S2, S3. Okay. Meanwhile, the total angular momentum looks like the equation for a sphere. S1 squared plus S2 squared. Where is that? Here. S1 squared plus S2 squared plus S3 squared equals a constant. So let's draw these two equations in the S1, S2, S3 space. So S equal to a constant gives us a sphere in blue, and energy equal to a constant gives us an ellipsoid in red. And our solution needs to stay on the intersection of these two surfaces. It needs to stay on both surfaces for all time. The intersection of these two surfaces is two circles, one on top and one on bottom. So whichever surface you start on, whichever circle you start on, you need to stay on for all time. And so what the solution does is it rotates around these circles with whatever its initial velocity is. Okay? So the angular momentum vector in fixed body coordinates is going to travel around these circles as time goes on in a periodic orbit. Now, what that tells us is that in fixed body coordinates, the angular momentum vector precesses around the axis of rotation.
Now, if you switch back to standard coordinates, the angular momentum vector stays fixed, and the angular velocity vector is going to rotate around the angular momentum vector. And this is called precession of the angular velocity vector. So going back to our picture, we have now proven using the lax pair and using a bit of a geometric argument that the angular velocity vector of a rotating top spins around the angular momentum vector as time goes on. Okay? So this was studying the Euler top, which is without gravity. But if you want to study other kinds of tops, as long as you have certain ratios between the moments of angular inertia, moments of inertia, then you end up finding that you still get a lax pair for the system. So this is, for example, the Lagrange top and the Kovalevskaya top, which you can look up. You still get a lax pair for the system, and therefore you still get the precession of the angular momentum vector. So you can study even situations where the top is rotating on a table, as long as the moments of inertia are in a specific ratio to one another. So I highly recommend you look this up. It's really interesting. And it's cool that we can study the rotation of a top using these lax pairs. Okay. And all kinds of different math came up, even like stuff like Lie algebras in the process. Okay, so this is where I'm going to stop for today. In the next part, we'll talk about the final example, the Toda chain, and then we'll move on to talking about quantum mechanics. So thank you very much for listening to this talk recording. I hope you enjoyed it. Feel free to ping me in the Math Discord and ask questions if you have any more that come up. And I'll see you for the next part. Thank you.